Okay. Any questions about the way to determine RNS from yesterday? So obviously for next Monday's exam, that's going to be a big part of that exam is determining RNS. But what we've done so far is to look at a molecule with one chiral center, or if we've had a molecule with two chiral centers, we haven't talked about the entire molecule. We've just talked about determining RNS for those two chiral centers. So now we need to expand into, well, if you have one chiral center, the total number of stereoisomers, the number of stereoisomers is always going to be 2 to the n power, where n equals the number of chiral centers. So when you just have, or chiral centers, chiral carbons, when you only have one chiral center, then you only have the possibility of 2 stereoisomers, a D and an L or an R and an S. But now when we go to, let's say, 2 chiral centers, we're now going to end up with the possibility of 4 stereoisomers. And I should say that the maximum number of stereoisomers, because there are molecules that have 2 chiral centers but only have 3 total stereoisomers, and so we'll talk about that. So let's do an example of that. So let's draw a molecule with 2 different chiral centers, and then let's write all 4 possible molecules. And we're going to do this, let's do this in the Fisher projection. And let's start with something like where there's a hydrogen here, a CH3 here, an OH there. We'll put a hydrogen there, we'll put a Cl, and maybe we'll put another CH3 there. Okay. So we'll start with this molecule that has one chiral center. Or sorry, 2 chiral centers.
Is there an easier way to kind of determine whether something's got more than one chiral center, or is it just looking at each junction and adding?
So, not necessarily except the mirror plane. So when we look at this one, we'd have to look at each of these 2 carbons and say hydrogen, methyl, OH, something different. So that definitely has 4 groups. This carbon has 4 different groups. Can I pass a mirror plane down through the center of the molecule? Well, actually, in this case, I'd have to pass a mirror plane through either one of those 2 carbons, cut the molecule in half. Since I can't do that, then those are chiral centers.
And is it cutting that mirror plane horizontal or vertical?
Whatever way I can cut the molecule in half. So we'll deal with this one in, well, let's just say, how do we want to do this? So for instance, this carbon right here, that carbon's not chiral because it's got the 2 groups that are the same. I can cut that carbon in half with a mirror plane of symmetry. Now, cutting that carbon in half is different than cutting the molecule in half, which we're going to get to. So, in this case, the only chiral center in this molecule is this one. That is not a chiral center. So you kind of have to just look at the 4 groups that are attached. If it's a ring, you have to go off. If you're doing RNS, you have to determine 1, 2, 3, 4. If you get 2 groups and they end up tied, then that's not a chiral center to begin with, and there is no RS.
So it's just the process of eliminating.
Right, in the molecules we've done, when I write it this way, those 2 will be chiral centers. Because if they're not, then there's no problem to do. And for the cyclohexane rings, usually the carbons that have a group off of it are going to be chiral as well. But now what we have to do today is distinguish between a chiral carbon and a chiral molecule. So in this case, these two carbons in the Fischer projection are chiral because they've got the 4 different groups attached to it. Let me start with what is the top carbon and what is the bottom carbon in terms of R and S. So I'll give you a minute to take a look at what is the top carbon? Is it R or S? Is the bottom carbon R or S? And remember that the Fischer projection looks like that. Horizontal, bold, dashed, vertical. Do we have an answer? Do we not know where to start?
Both of them or just the top?
How about the top one? What do you think? Agree?
R.
Right now you're outnumbered.
I got a question.
Yep.
Because you got the chlorine, does that go in one or the oxygen?
So let's break this carbon up. So what's attached? So down here, here's that top carbon. What's attached to the carbon? A carbon, a hydrogen, an oxygen, and this carbon. So the chlorine doesn't play a role yet. So that means what's number 1? Oxygen, and number 4 is hydrogen. So now I'm going to compare a CH3 to a C with more than just 3 hydrogens on it. So that's going to make this one number 2 and this one number 3. And when we take a Fischer projection, it's usually to our advantage to try and orient the hydrogen on the vertical position, because then it's away from me on the dashed line. So that now I can say, okay, going from 4 is dashed, so going from 1 to 2 to 3 is clockwise. So that top one is the R. And then for the bottom one, what is it? What do you got? S, we agree. So there we're starting, chlorine's 1, hydrogen's 4, CH3 can't beat a C with more than that on it. So this is 3 and 2. So for the bottom carbon, again, number 4 is on a dashed wedge. So going from 1 to 2, 3 is counterclockwise. So that's an S.
Going from the first structure to initial projection, how do we know that the vertical line is dashed horizontal?
Because that's the way a Fisher projection is defined.
The first structure then?
The first structure, meaning this entire one.
Yeah.
So there's a couple ways you could draw this, but what I like to do is to say that basically these two positions are dashed. The horizontal positions are definitely bold, and then for the middle one, we'll just put it in the plane.
Could not be any other animation.
No, other than you could say that this position in the middle is dashed, and if it is, then looking at it, so here's my hydrogen, and then it's like this, and then this one down here is going to be like that. So it's going to be like a C shape. If you look at it that way, if you put the dashed and then the other dashed, so it's just easier to say for this structure, I'm going to consider that one in the plane. But the two other vertical positions are definitely dashed, and everything that's horizontal is bold. So that's the way that structure is defined. Down here, when I'm doing it, I'm basically breaking it up into the dashed vertical, bold horizontal. So that's the way we're going to define it. So why did we do that? Because now what we're going to do is we're going to keep track of the structure as well as the configuration on each of the two carbons as we draw 3 more stereoisomers. Because this one is number 1, there's 2 chiral centers, so that means by our formula there's a maximum of 4 different stereoisomers. So what I want to do is I want to draw them out. So let's start with what is the mirror image of that molecule. And we can draw the mirror image by basically saying here's a mirror plane. So the OH is going to be on the left and the methyl group is going to be on the right for the top carbon. So if you just take a step back, looking at the top carbon through this mirror plane, you can see that they're mirror images of each other. Hopefully. Can everybody see that? That for this one, if this is the mirror plane, the OH, the CH3, and the H are mirror images of each other. And then we can do the same thing for the bottom carbon, and we can do that. We can make the bottom carbon the mirror image. So I've just made the mirror image of the molecule. For Fisher projections, it's nice because I don't have to, basically the mirror image of the Fisher projection is another Fisher projection. The mirror image of, let's say, a tetrahedron, if I wanted to draw its mirror image, I'm going to have the bonds in different positions. So here would be the mirror images of a tetrahedron, but for a Fisher projection, the mirror image is another Fisher projection. So I'm going to call this molecule A and this molecule B. Everybody with me, because we're going to step through this. Not necessarily as quickly as we could, but we're going to step through this in order to generate new stereoisomers that I have to give names to. And there's different ways I can define this depending on what I'm looking at. So everybody okay that I've just drawn the mirror image? The B is a mirror image of A. If you're not, you got to yell. So here's my next question. My next question is, what is the configuration, R or S, of the top carbon and the bottom carbon in B. That was fast. I'll ask you why it was fast in a minute. Got it? Okay, what's the top carbon? And bottom carbon? Did anybody get that in 2 seconds? Okay, exactly. So you can answer that question really quickly, because if two molecules are enantiomers, if they're mirror images, there's two definitions of enantiomers. The one is that they are non-superimposable mirror image isomers, which is what these two are. They're mirror images, and if I slide them together, I can't superimpose them. But an alternative definition is that when you have a molecule with any number of chiral centers, if each and every chiral center in the molecule is opposite in both structures, they're also enantiomers. So if I just gave you a molecule and said it's a 1R, 2S, 3S, you could write the enantiomer of it by saying it's whatever I said the opposite of. So 1S, 2R, 3R. So we can determine that they're enantiomers by looking at the chiral centers and saying, okay, the chiral centers then are each chiral center's opposite in the two molecules. That's also a definition of enantiomers. So A and B are enantiomers because they're mirror image isomers. So that's why I had you initially determine R and S, because we need this alternative definition. We okay with that? All right, next. Next, I still am missing two structures because I could have up to four. So how am I going to generate my next structure? Anybody have any suggestions? Just flip it up again. I don't know what that means. Tell me what group would go here. Right, oh, sorry. Which group would go here? Okay. Group on the left? Group on the right? Wait, with chlorine. Oh, so you want to take the molecule and you want to do it this. I don't want to do that. And I'll show you why in a minute, why I don't want to do that. So let's not do that for the moment. Because I actually want to keep the top carbon having the same groups. So, no? Okay, stop right there. So you're using the RS. So one of these carbons would be carbon 1 and one of these carbons would be 2. So what you're saying is, like for this one it's 1R, 2S, and for this one it's 1S, 2R. So what would be the other combinations? And you're saying, well, just from R and S, another combination would be both of them are R, or both of them are S. In other words, take the top carbon. Well, I don't want to rotate anything. Well, I don't want to rotate because when I rotate, I don't change the configuration. I want to just write a configuration. So I want to, let's take that example. Let's write RR. Is everybody agreed that RR is going to be different than RS and SR? So let's write the RR. Let's write the RR configuration for this molecule. So the R is going to have the CH3, the H, and the OH on top. And how was I able to draw that so quickly? Because I just looked at the first one and said, okay, that carbon's R. So I want to have the R, and then down here I want to have the second carbon R, so what should I have there? What should be on the left? Chlorine should be on the left, then methyl, and then hydrogen. So all I'm doing is looking at the R and the S configurations from the original two molecules. So this is a different structure.
So that one's not open.
Exactly. So we're agreed that this is a different structure. Now, if you don't want to do R and R, say R and R, what I could have said is, let me take the top carbon's configuration from A and the bottom carbon's configuration from B, and let me put that together to form that new structure. And we might as well draw the fourth one then, D. So what do we want D to be? S and S. So write the top carbon's configuration as S. So again, if I'm writing the top carbon's configuration as S, that's going to come from B. And then the bottom carbon's configuration from S is going to come from A, molecule A. So let's take a step back here. What did we do? We're now working with a molecule with two chiral centers. The formula, the maximum stereoisomers, the formula says that if you have two chiral centers, you should have 2 to the n, or in this case, 2 to the 2 squared, maximum number of stereoisomers. So for any molecule that has two chiral centers, there should be 4 structures. There should be 4 stereoisomers. We started with A, determined its configurations were R and S on top and bottom, and then we wrote the mirror image of both of those to make B. So the relationship between molecule A and B is that they are enantiomers. They are non-superimposable mirror image isomers. So A and B are enantiomers. We also then said, okay, if molecules are enantiomers, every single chiral center in those two molecules will be opposite in configuration. So if you start with RS, you're going to end with SR. And so I could give you the letter combinations and you could tell me, well, they have to be enantiomers because every single chiral center has an opposite configuration. Is there another pair of enantiomers in those four? So of A, B, C, and D, we said that A and B are mirror images because they're mirror images, but they also go RS to SR. Is there another set of enantiomers in this set of four? C and D. So C and D, if I draw my mirror plane here, we can see that the top carbon is a mirror image of each other. The bottom carbon is a mirror image of each other, but I also know that it goes from RR to SS. Every single chiral center has been changed. And so C and D's relationship is they are enantiomers. So A and B are enantiomers and C and D are enantiomers. Everybody with me? So, try and be psychic. What's my next question going to be? Or what should your next question be? For stereoisomers. I could ask that question, but that wasn't the question I had in mind. Eleanor, you kind of got at it. When you were looking at C, when we first drew C, what did you say? You're too young to do that. I think you said so C is not a mirror image of A or B. So C is not an enantiomer of A or B. So what is it? It's diastereomer. So what are diastereomers? So B and C are diastereomers. So in other words, we need a new term. So what are diastereomers? Well, my definition of diastereomers are that they are non-superimposable, meaning that you can't superimpose those, but they're also non-mirror image isomers. So diastereomers are non-superimposable, non-mirror image isomers. That's my technical definition of what a diastereomer is, which isn't helpful, right? Because non-mirror image, non-superimposable isomers. But what practical information do I have? Because what we're going to do here is we're going to work our way up where I'm going to give you two molecules and I'm going to say, what are they? Are they enantiomers? Are they diastereomers? Are they mesocompounds, which is another term we'll have to define? Or are they none of the above? So what practical information about B and C could you use to say, well, those are diastereomers? So along the same lines as saying, what was the difference between enantiomers? Can we use R and S to define diastereomers? Enantiomers, we said what? Every single one was opposite. Is that true between B and C? No. One set is opposite and one set is the same. So if we look at the chiral centers then for diastereomers, if we look between B and C, the top ones are different, but the bottom ones are the same. So practically we could say diastereomers have at least one carbon having the same configuration and at least one carbon having opposite configuration. So at least one the same, at least one opposite, because that's the broadest definition, that'll cover everything. So B and C are diastereomers. Is there another diastereomer to B? D is also a diastereomer to B. So not only are B and C diastereomers, but B and D are also diastereomers. And if I wanted to look at A, what's a diastereomer to A? C and D. So is everybody okay with that, with those practical definitions? So you can say at least one chiral center is the same, at least one opposite for diastereomers, but for enantiomers, every single chiral center has to be opposite. Now, in these four molecules, it's more likely that a molecule will have a diastereomer than it will have an enantiomer. Right, because it's got two diastereomers but only one enantiomer. And that gets even more diastereomers if we went to like 3 chiral centers. Because if we went to 3 chiral centers, we would have 8 possible structures. And so for every molecule, it would have one and only one enantiomer, but it would then have 7 other diastereomers. So there's more diastereomeric pairs in a set of stereoisomers than there are enantiomers, because each molecule has one and only one enantiomer, but it's got a lot more diastereomers. So when we're starting to expand here, we're starting to expand and say, okay, we could have a maximum of 2 to the n number of stereoisomers. If I gave you 2 a pair, what are they? Enantiomers or diastereomers? And so you could determine R and S for each chiral center. There's going to be systems where that doesn't work. So I like the practical definition of, let's compare each chiral carbon, determine whether they're the same or opposite, and then apply those definitions. All opposite, enantiomer. One same, one opposite, diastereomer. You with me? I know I moved to cyclohexanes. We'll go back to Fisher projections in a minute. So my question between these two molecules is, are they enantiomers or are they diastereomers? I've got diastereomers on the table. That was fast, wasn't it? Don't worry, you're okay. Anybody else have come up with an answer? Agreed? So one of the things we could do here is we could write like we did yesterday. We could imagine ourselves up here looking down on the ring, and we could draw the two flat cyclohexanes. And then we just have to realize that in this case the chlorine's above the ring, the bromine's above the ring, over here the hydrogen and the bromine are above the ring. So we could write it like this. Aria. I said I'd write it down, I didn't write it down. Aria, how were you able to come up with that so fast? Okay, stop right there. So the Cl and the H were flipped or interchanged. What does that mean about their configuration? So what we have to do is we have to remember talking about group switching. What happened when we only switched two groups once? The configurations were opposite. So if I switch two groups one time, those two chiral carbons have opposite configurations. If I have to switch them an even number of times, then those two chiral centers have the same configuration. So for this one, we could say, okay, since going from here to here required one change, that means that the top carbon is opposite. And could you do that down here in the flat cyclohexane? Yeah, you could do the same thing. You could say, well, I need to interchange the chlorine and the hydrogen one time to go from here to here. And so the top carbon is going to have the opposite configuration. If I had to make two switches, they would be the same. And if I had to make 0 switches, since I'm considering 0 an even number, it would be the same. Does that make sense to everybody? So what we're going to do is we're going to compare each carbon individually and say, is it opposite same? So for the top carbon, they have the opposite configuration. How about the bottom carbon with the bromine? Same or opposite? Same? So I don't have to make any switches in order to get from here to here, I don't have to do any switches. So that means the bottom carbon has the same configuration. Over here, same thing. Bottom carbon is the same. So what is the relationship then between those two molecules? One chiral center is opposite and the other is same. That makes these diastereomers. You want another? I can do this all day. But just like yesterday when we went like 3/4 of the class with all S's, and then we finally got around to R's, when I make these up, there's no rhyme or reason. Okay, I'm not trying to, I will later on try and make something So here are two Fisher projections. Are they enantiomers or diastereomers? Actually, there's a third choice now. They could be the same. They could be exactly the same molecule. Let me do this one in my head. You may be right. What's my goal? My goal is compared to top. Now, let me take a step back. When you start one of these problems, here's what we have to do. We have to make absolutely sure that the top carbons are the same and the bottom carbons are the same. Because what I like to do is I like to take one of those two molecules and I like to rotate it 180 degrees so the chlorine's on the bottom carbon and the OH is on the top carbon, so I can't compare top to top and bottom to bottom. And also this idea of saying, well, how many switches do I need to make? That only works if the molecules are in exactly the same orientation. So if I put the bottom carbon as the top, you would have to take the molecule and you would have to rotate it 180 degrees so that now it's lined up. But we don't have to worry about that in this case because top carbons are the same, bottom carbons are the same. They have the same things attached to them. So what is the top carbon? Are the top carbons the same or opposite? Actually, if I'm only concerned about same or opposite, I only need to put the hydrogen on the dashed line if I'm going to determine R and S. And hopefully what you're kind of seeing here is R and S, you can do R and S, but it's going to take you a lot longer than just determining whether it's the same or opposite by one of two things. So, a couple ways I can look at the top carbon and determine whether it's the same or opposite. What did you do, Cameron?
There were 2 switches. So,
Okay, so you want to go from here to here, and then you count the number of switches that you need to make. So what do you want to switch first?
the CL and
So I'd have to switch the CL and the CH3. That's, you'll see in the answer keys, I write that down as one switch. Am I lined up yet? The methyl groups are lined up, but not the chlorine and hydrogen. So I now have to make one more switch of chlorine and hydrogen. And so if I make the second switch, now the methyl groups are lined up, the chlorine is lined up, and now the hydrogen is lined up. So if I want to go from left to right or right to left, doesn't matter, I have to make 2 switches, which means that the top carbon has the same configuration. Does that make sense? Did anybody do it a different way? Hold on, let me write it out, and then you can tell me what you did. Okay, what'd you do? Okay, so you determined R and S. Okay, so you did R and S, which will work, but not all the time. We haven't gotten to the time when it won't work yet. So it'll work as long as the compound is at meso, and we need to talk about what a meso compound is. Did anybody do it a different way other than like switching the groups? So here's another way to do it. Another way to do it is this. Remember that in the Fisher projection, remember you have a Fisher projection. Here's my Fisher projection, right? So the Fisher projection, here's the group that's down, here's my 3 up. I don't know if this would make it better, probably make it better if you do this with the whatever school that is. I think it's Texas, right? Hook 'em horns, unless that's some sort of, I don't know. You should probably not make hand gestures, because if you're not up on your hand gestures, you're going to make one that's going to get you in trouble. But here's a Newman projection. So I can rotate that this is a Fisher projection. I can rotate it this way, but I can rotate it this way, and it's a Newman projection. So in other words, I can rotate things. So I could rotate let's see, I want to line up the groups, right? So what if I rotate this methyl group here, the chlorine here, and the hydrogen there? So I do a rotation, which is basically a vertical Newman projection. Then the methyl group goes here, the chlorine goes here, and the hydrogen goes there. Did I line up the molecules so that they're the same? Yes. So by rotation, I'm showing that the top carbons are the same. The question is, what if you try and line up the groups and they're not the same? What will they look like? So if I tried to line up, let's just make it simple, A, B, and C. If I rotate and I can line up 2 of the groups, but I can't line up the other 2, so I can line it up so that the A's are in the same position, but the B and the C aren't. what's the relationship between those two chiral centers? Oh wait, they're the same. So I rotate them and I can't line up B and C. Then what are they? They're opposite, but in terms of C here, B there, A there, they're enantiomers, but between these two chiral centers, what can I see? They are, what did I just draw here? A mirror plane. So these two carbons, if you can line up two of the groups, but not the other two, they're automatically going to be mirror images. And if those two are mirror images, then those two configurations are. How did we start? We're looking at the individual carbons first, so either I'll line them up and those two carbons will have the same configuration, or those two carbons will have, if they can't be lined up, they're going to be mirror images, which means they're going to have the opposite configuration. And so if you can line up only two of the groups, you should see the mirror image. You should see that those two carbons are mirror images. So that means in this case they would be opposite. Well, that's sort of what I was going to say, but we only want to use enantiomers to look at the overall molecule now. When we're talking about individual carbons of the entire molecule, they're either the same configuration or opposite configuration. Because then once I determine for all of the chiral centers the pattern of same or opposite, then I determine are they enantiomers or diastereomers. Or now, the same. If all the chiral centers are the same, the molecule's the same. So what about the bottom carbon then? Same. So we could get that by switching or by rotating. Part of my job is this. So you might say, what's his point? You'll say that a lot. I will say, what's my point? Then I'll have to think about what is my point. What is my point? That was just for comedic effect. My point is this. I'm trying to give you as many different ways as possible, and then you have to figure out which one works best for you. And in some cases, RNS will always work, except we'll get to it in a minute when it won't work. So you have to be able to use multiple methods in different circumstances. But whatever way works for you is, what you're going to use. How are you going to know a method works for you or not? Right? Do we want to be determining that next Monday? No. Right? We want to know that far before Monday, what method works best. So for the bottom carbon then, it also has the same configuration. How do I know that? Again, I can switch. How many switches did it take me? In this case, it would take me to switch H and OH, and that would line up the H, and then I'd have to switch the OH and the CH3, so it would take two switches. Or if I wanted to rotate, I could rotate this hydrogen over here, the OH down here, and the methyl there. Now all three groups are lined up. When you rotate, you're not changing anything. When you're switching, you're physically changing it. But if you switch twice, your back door you started, which is why they have the same configuration. So when all the chiral carbons are the same, it's same molecule. So right now our choices are they're enantiomers, diastereomers are the same. So if I give you a pair of molecules, that's what you would do. So notice, just like we did R and S yesterday, it seems like such a long time ago. We did Fisher projections. We could do tetrahedron. Tetrahedron are boring. I'll show you what you have to watch out for tetrahedron. So for these tetrahedron, and normally it's A, B, C, and D, where it's same, or they're enantiomers, diastereomers, same or meso. So those are your four choices. So this exam might be a lot of multiple choice of R and S, A, B, C, D, maybe if I have you rank groups. But it just so happens that is the way it's working out. I don't know that I'll use a Scantron for it, but I could. If I really want to grade it like instantaneously. So this one, I'm stuck. But let's see, I've got four choices, A, B, C, D. I don't know what meso is, so let's throw that one out. I'm down to same enantiomers, diastereomers. Can I throw another one out? I need to guess. Hopefully you don't need to guess, but if I needed to guess, I have four choices. I throw out meso. Is there another answer I can throw out for this problem that it absolutely isn't relevant? Diastereomers. Why diastereomers? Why can I throw out diastereomers? Why is diastereomers not even an answer for this one? Okay, so we didn't say that before. We didn't say what you needed to have diastereomers. You need to have at least two chiral centers for two molecules to be diastereomers. So if you're down to a single enantiomer or single chiral center, they're either the same or enantiomers. That's it. And meso will also need two chiral centers at least. So you can be a little strategic in terms of saying, oh, well, if it's a single chiral center, it can never be diastereomers. So now you're down to same or enantiomers. How about this one? Not if you don't have to put the hydrogen going backwards if you're not going to use R and S. If you're just going to visually compare the two molecules and line up the groups, you're either going to line up all four groups or you're going to only be able to line up two groups. So if you can line all four of them up, they're the same. So they have the same configuration, which means they are the same molecule. If you can only line up two of the groups, then they're going to be enantiomers, and they have opposite configurations, so they will be enantiomers. If you're going to switch one into the other, the tetrahedron have to be in exactly the same orientation. So it would take two switches, right, to go from left to right, or right to left. The way I did it in my head is I looked at this and said, oh, the OH is in the same position. So if I rotate the methyl group down here, the chlorine over here, and the hydrogen up there, that's not helpful. If I rotate in the opposite direction, then the other three groups will line up. So now all four groups are lined up. So you don't have to do R and S. And so far you can do R and S for all of these, and you would get the correct answer. But you don't have to do R and S. Now, there's got to be a time when you have to do R and S, right? That's just the way it is, right? There's going to have to be a time when you do R and S. When is that time? That time. So in other words, if I give you molecules that aren't in the same orientation, like a Fischer versus a tetrahedron, unless you can see in your head how to make the tetrahedron into a Fischer projection, or turn the tetrahedron, or they just say tetrahedron into Fischer, or Fischer into tetrahedron, you're going to have to do R and S. And you might say, well, I can do this if I have my little model set to do that with, which is great for, practice. But unfortunately, there's not a test. I mean, I could let you use models. As long as you didn't play with the models and you're answering questions, that's okay. But somebody usually plays with the models more than they answer questions, and they get upset with me. That's happened. But if you go on and you take another test, like at the end of the semester, the ACS test, or if you go on and take an MCAT or anything like that, any kind of pre-health professions test, they're not going to let you use models. Which is why I kind of, you have to be able to do this in 2 dimensions, which is why I'm showing you the group switching technique, because this group switching technique will let you get R and S without model, or without having to visualize it in 3 dimensions. You'll still get the right answer. No, you've got to line them up. So in other words, you have to say how many switches does it take to move this one to line this one up with this one. Right. If it takes 2 switches, it's the same. If it takes 3 switches, it's still an enantiomer. So that's where, when we talk about group switching, if you have to switch, if you switch groups an odd number of times to get the hydrogen or the low 4 priority group away from you, if you have to make an odd number of switches, if you stop then and determine clockwise or counterclockwise, you're going to be wrong. Because when you did the 1 switch, you changed the chiral center, which I said was an option, right? You could do that. You could say, well, I'm just going to make 1 switch, put my hydrogen away from me, I'm going to determine R, and then I'm going to write down S. If your mind works that way, I'm not going to mess with it. Well, it may cause you problems later on. So that's why we always do 2 switches, because then whatever we determined was the original answer. So with this, even number switch, same configuration, odd number switches, opposite. And if you don't want to switch, then you can try and rotate the molecule to get it in the same. It'll either be the same or you'll only be able to line up two of the groups. Or you'll line them up in their mirror images. For this one, you're going to have to do RNS. Unless you can switch, or unless you can rotate a tetrahedron into a Newman projection. Now, I can show you how to do that. Computer science students built us a virtual reality molecular modeling set with the $500 virtual reality goggles and everything. And one of the things we were working on was, that's a tough move. To go from Fisher to tetrahedron or vice versa. But having spent way too much time in that virtual world, this is your Fisher projection with the silver and no ball sides. That's your Fisher projection. So let's see, from your standpoint, what is that? Where's the silver? Left or right? Right? And then we'll call it A and B for the two other ones. Now, if I want to plop this down on the table in a tetrahedron, here's what I'm going to do. So what's bold? Let's see, is that even? Do I have to interchange the bold, move the bold and the, yeah. Bold in the plane. So where did the silver ball go? It's to your bold right. It's to the right and bold, right? So that's where the silver went. And then where did the no one go? It went over here, right? And then the A that was on top is still A. And now the B that was on the bottom goes in the back. Going from right to left, I can see it. But I've been doing this a long time. A long time. Could you see though that here, that going from, let's say, left to right, that here's my tetrahedron with my silver. All I've got to do is just do this. All I got to do is just, it's flat, so all I got to do is do that. So the silver, so these two basically stay the same, and then these two, the A, these two positions go into the verb. So it is possible to either start with a Fisher and lay it down as a tetrahedron, or start with the tetrahedron and just lift it up. So you could get those two. You could interconvert those two. And if you put them in either form and they're both in the same form, now you can group switch, or you can rotate. But if you don't, then you got to determine RNS. So when you only have one chiral center, If I give it to you in the same orientation, you can switch or rotate. If I don't, you're pretty much stuck in doing R and S unless you can manipulate that structure. And if you don't have, like if you want a chiral center with 4 different balls attached to it, to use for any of this stuff, let me know, and I don't know if I got all of them back last year when I gave them out to people, but I'll find more. So if you want one of those, let me know. I can bring it to class tomorrow, or you can stop by and grab one to use as you're practicing for the exam. All right, so where are we at here? Let me think through. So right now, what we've done, we can tell the difference for fissures, for chair cyclohexanes if we put them flat, and for single carbons, we can determine whether they're the same, whether they're enantiomers or diastereomers. But we have one more stereochemical relationship left that we have to define. And this will only occur with 2 or more chiral centers. And that is meso. So let's okay. Meso. What is a meso compound? Let's develop a meso compound. So from a Fischer projection, let's say I have this Fischer projection. Of hydrogen methyl OH attached to each of the 2 carbons, and I start with this molecule. Now let's write the mirror image of this. Let's write the mirror image of that molecule. Okay, just like I started with. Start with the molecule, write its mirror image. And let's do the same thing that we did before. So let's take the top configuration on the left, the bottom configuration on the right to write molecule C, and then we'll take the opposite to write D. So we'll take the top carbon's configuration from the first molecule, and we'll take the bottom configuration off the second molecule to write compound C. And then for D, what can I do? I could just write the mirror image of it. So exactly what I did before. I started with the structure, and I've got 2 chiral centers. That means I have a maximum of 4 possible stereoisomers. And so now I've written the 4 stereoisomers. Anybody concerned that those two carbons are not chiral centers? Well, if we're uncertain, we could take this, we could say, okay, what's it got attached to it? A methyl, a hydrogen, an OH, and not a methyl. So it's got four different groups. This carbon, same thing. It's got 4 different groups. So those are definitely chiral centers. What's the relationship between C and D? They're enantiomers because the way I drew them as mirror images. What's the relationship between A and B? Same. That's the trick question of the day. What's the relationship with between A and B? They are mirror images, correct? In order to be enantiomers, they have to be non-superimposable mirror images. Now, for the A and B, can I superimpose those structures? Not if I just take them and slide them this way. But if I take this one and I rotate it in the plane of the paper, so I grab it, I rotate it 180 degrees, what's it going to look like? Well, all the methyl groups are going to go on from right to left. The OHs are going to go from right to left. They're going to go from left to right. And the hydrogens end up in the same place. So if I make a 180 degree rotation, I'm going to make this molecule, and what is that? It's the same as A. It's superimposable on A. So A and B are not enantiomers. They are the same. So this is a new kind of compound. Because my definition of this would be, these are molecules with chiral centers, but they're superimposable on each other. Technically, are those molecules chiral? We have to go all the way back to Monday, when we originally defined chirality and said that the molecule, if a molecule is, we never said this, but we will now. If a molecule is superimposable on its mirror image, it can't be chiral. Because the definition of chiral is that you have a mirror image and it's not superimposable. But what if you have a mirror image that is superimposable? You ain't chiral. So what features then of objects that are superimposable on their mirror images, what features do they have? Well, if you disregard the writing, because it's a 2-soda class day, could be 3. If you disregard the writing and the cap on top, then those two are mirror images, right? But are they superimposable? Yes. Why? Because what is there through the center of that molecule, the center of that can? There's a mirror plane of symmetry. I can cut the molecule in half. Yes? Good question. So why are C and D superimposable? Are we agreed that if I try and take them and slide them this way, they're not? Okay. You want to rotate it 180 degrees? Let's rotate it 180 degrees. So the H is, now this methyl group on top comes over here, right? So actually, sorry. This methyl group when it's switched over comes down here. So when I take this one and I rotate it 180 degrees, the methyl group ends up there. This OH, when I flip it 180 degrees, it ends up on the bottom. So these groups move from top to bottom, but they also move from left to right. So the bottom one, the methyl group, ends up, when it rotates, it ends up here, and the OH ends up there. So when you rotate it 180 degrees, the top and the bottom, they interchange, but they also interchange from left to right. So when I do that, what do I end up with? I actually end up with the same molecule in this case. We're not going to talk about this other than for me to say this is actually what's called a C2 mirror plane, meaning that it's a rotation of 180 degrees. That the 2 is 360 divided by 2 is 180 degrees. So the key thing is I can rotate that all day long and I can't line them up. So those two are truly enantiomers. But A and B are the same. So remember how I've been saying the 2N formula gives you the maximum number of stereoisomers? How many individual stereoisomers are there from A to D? 3. So there would be a maximum number of 4, but if you have a meso compound, it reduces it by 1. So in this case, all we have is a meso, and then we have the 2 enantiomers. Those are the possible stereoisomers here. Where's the mirror plane for A and B? Vertical? I'm not drawing anything. Would that cut the molecule in half? No. And if it did cut it in half, what would happen to those 2 carbons? They aren't chiral. Okay, the definition of a meso compound is it's superimposable on its mirror image, but it has to have chiral centers. If it doesn't have chiral centers, it's not meso. So that mirror plane doesn't work. So how's the mirror plane got to be drawn? This way. Did it go through any chiral centers? No. Did it go through the molecule? Yes. So you can also define a meso compound as being a molecule with chiral centers and an internal mirror plane of symmetry. And this is what's new. Before, when we've had a mirror plane of symmetry, it's cut through a carbon so that carbon's not chiral. But now I'm talking about the whole molecule. So if the mirror plane cuts through the molecule but leaves chiral centers intact, it's now a meso compound. 2 definitions one more time. They are, a meso compound it has chiral centers, but it is superimposable on its mirror image. So the first part's critical. It needs to have chiral centers. How many? 2 or more. At least 2. So a meso compound has chiral centers, but it's superimposable on its mirror image. That's like a technical definition. The practical definition is that a meso compound has chiral centers and an internal mirror plane of symmetry. But if that internal mirror plane of symmetry cuts through any carbons, they ain't chiral anymore.
Then you have internal mirror plane that does not.
Well, it can't, for meso, any chiral centers that, or any carbons that mirror plane cuts through would not be chiral. So if it cut through carbons, there still has to be it has to be two chiral centers in the molecule. Right, because they're not chiral anymore. The molecule has to have chiral centers. I'll show you an example of that where it may cut through carbons, but those carbons aren't chiral. Okay. So that's the operational definition of a meso compound. It's got to have an internal mirror plane of symmetry, and it has chiral centers.
If you say the internal plane, mirror plane of symmetry, and not cut through chiral centers.
Right. There still has to be chiral centers when we apply that mirror plane of symmetry. In this example in A, what's happening is here's my mirror plane of symmetry, but those two chiral carbons are not cut through, so they are chiral. They remain chiral. If the mirror plane of symmetry was like what you want at the beginning, vertical, there would be no chiral centers, but that's not a mirror plane of symmetry. I'll give you a couple examples. But before I do that, does a meso compound rotate plane polarized light? It can be a rhetorical question that I will answer, but what do you think? Let me ask a second question. In order for a molecule to rotate plane polarized light, this is a statement. The molecule has to be chiral. Are meso compounds chiral? That's a good question. Just because you have chiral centers, is the molecule overall chiral? What does it mean to be chiral? Going all the way back to my hands. My hands are chiral. Why? They're mirror images and they're not superimposable. Is a meso compound superimposable on its mirror image? Yes. Now, C and D are full-fledged chiral molecules. They will rotate plane polarized light. 1D, 1L because they're enantiomers. But for the meso compound, since it's superimposable on its mirror image, it is not chiral. So again, weird thing about meso compounds. They have chiral centers, but they don't rotate plane polarized light. So if a molecule is superimposable on its mirror image, it will not rotate plane polarized light. But it still has chiral centers. Now C and D will because they're both chiral. They are not superimposable on their mirror images. So actually what we call these four compounds, and let's see, now's my time to go back and remember what I told you on like Monday. I said, oh, we'll come back to this. And I got to remember exactly what we'll come back to. Here's what we'll come back to. I may or may not get this exactly right. That's the idea of a good story. So, when Pasteur determined, or was the one who was determining chirality or developing chirality, developing the idea, He did this based on the crystals that were found in the cork of the wine, being in France. And in the corks of the wine, and I'm repeating what I said on Monday, but it was Monday, there were crystals that were formed, and so he took tweezers and he pulled them all down and put them on the table, and then looked at them under the microscope. Now, the molecules that he was looking at was what was called tartaric acid. Tartaric acid has, if not this exact structure, there may be CH3s for where the H's are, or you can fact check me and see what it is, but it sort of has this kind of structure. I should probably fact check myself. But it has this kind of structure, which is exactly what I drew to begin with. So for the tartaric acid, what they found was that there were crystals that you could align that were mirror images of each other. They were chiral. They were not superimposable on themselves. But then there were crystals that were perfectly symmetrical, that when you lined them up, they were mirror images. And so tartaric acid, if it has this kind of a structure, it has two chiral centers. It has now two other stereoisomers, and the two other stereoisomers, if you have, the reason it's tartaric acid is because it's got two carboxylic acid groups that we'll sort of talk about in the future, but the three structures that are possible for tartaric acid are the first one, which is meso, and the other two, which would be mirror images, would be chiral and would be mirror images of each other. So after he pulled all these crystals down, he sorted them out painstakingly with tweezers, is the way the video goes. There used to be an old chemistry series of videos that was on PBS that I think you can still find online, but there's a professor at Cornell, Rode Hoffman, who won the Nobel Prize, and he comes out in the middle of the it's not Cuyahoga, it's Cayuga in New York in the wine region, and said, Pasteur found these, he painstakingly separated them with crystals with tweezers, and he found that there was one that wasn't chiral, and they called that racemic acid. And they called it racemic acid because it didn't rotate plane polarized light. The other two crystals, he found one rotated D, positive, one rotated negative, L, and we made a 50-50 mixture of them. He made a racemic mixture. The racemic mixture coming from the racemic acid of the original crystals. So racemic initially didn't mean mixture, it meant zero rotation of plane polarized light. So this is not chiral, so therefore it doesn't rotate plane polarized light. Again, Pasteur didn't know what the chemical structure was. All he knew is that the crystals in their shapes were mirror images or they were symmetrical. Well, if they're symmetrical, what does that mean? There's a mirror plane of symmetry that cuts through the molecule so that it's superimposable on its mirror image. So in tartaric acid, there is the mesotartaric acid, and then there's what we would call a DL pair. The DL pair meaning the two enantiomers were one's D and one L. And I'm sure there's some historical facts that I've either left out or, not gotten exactly right, but it's still a decent story. So, our whole idea of chirality came out of these crystals on this cork of the wine bottle. And because Pasteur saw them, but more importantly, somebody else had developed plane polarized light so that he could use them. But it wasn't until the early early 1900s that anybody knew what the carbon was tetrahedral. So all that was developed ahead of time. So how does this relate? Well, so for this molecule that I just wrote, the C and D are the DL pair, and A and B are the same, meso compound. So let's play the game, meso or not. I love meso or not. So the molecule is either meso or it's not. And the best things to start with are cyclohexane rings. Because part of this will get what happens if the mirror plane cuts through the molecule. It's got to cut through it may have to cut through a carbon. Okay, let's start with A. Meso? Agreed? Anybody want to say not? Does it have chiral centers? Is this a chiral center? It's got a methyl, it's got a hydrogen, it's got a CH2, and it's got a not CH2. 4 different groups. Same thing's true for the bottom carbon. Hydrogen, methyl, CH2, not CH2. So it's got 2 chiral centers. Where's the mirror plane? Did the mirror plane cut through any of the chiral carbons and then not making them chiral? No. So it's got chiral centers and a mirror plane. A is A's meso. What if the methyl groups were trans? Like in B, the methyl groups are trans. What if I made the methyl groups in A trans? Would it be meso or not meso? So E. Chiral centers? 2? Just remember, it's got to have 2 or more chiral centers. Mirror plane? Can't have a mirror plane with 1 up and 1 down. You can have one of those C2 axis of symmetry, but they don't count. It's got to be a mirror plane. So E, not meso. How about B? Not meso? Agree? Do we agree it's not meso? Anybody would say it's meso? Does it have chiral centers? Yes. Does it have a mirror plane of symmetry? No. Not with them being trans. No. You go till they come together. So for here, for instance, we'll do that on the next one maybe. So here we've got a methyl hydrogen CH2CH2, but remember, we've got to go what's attached to this CH2, another CH2. Oh, sorry, you don't. So this is CH3 and H, then CH2 versus CH2 tie, but now we go here, this group versus this group, are they the same? No. So if you go all the way around and come back and they end up in the same place, those two groups are exactly the same. But if you diverge any other point, it's not, then those two groups are different, so it would be chiral. So if there was a CH3 up here, then they would be the same and we'd end up in the same place. So actually, it would not be chiral. It wouldn't be a chiral center. Although, to be honest, it's going to depend on whether the groups are cis or trans. Because if one was down and one was up, they technically wouldn't be the same. But let's not worry about that at the moment. So we've got to go all the way around. And that's and now that we've done R and S, it hopefully is a little bit clearer than it was on Monday, that if you were going to do R and S, you just have to keep going until you find the point of difference. If there's no point of difference, it ain't chiral. C. Meso, not meso. Meso? Meso, yes. Meso, yes. Mel, bless you. Meso, yes. No, no, yes, yes, no, no. Uh-oh. We got yeses and we got nos. Chiral centers? That was a pretty aggressive no. What? So if we're looking, we got a methyl and hydrogen, then we go CH2, 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 I end up in the same place. So is this a chiral center? Is this a chiral center? Do the same thing, right? So this is the second trick question of the day. And I will get people on this. So make sure you don't get caught in this on Monday. But this doesn't have any chiral centers. How many mirror planes does it have? That's not helpful. We need a number. So I heard a 1, then I heard a 2. No. That's too many. 6 is too many. Mirror plane? Mirror plane number 2? Any more mirror planes? No. No more mirror planes. I can't, if I drew a mirror plane like this, this side and this side don't match up because the methyl groups aren't across from each other. So that's not a mirror plane. Hey, I want to cut through the center of the cyclohexane. You know, I'd accept that, so I'll accept 3. If you took it right through the center of the cyclohexane, the 2 methyl groups are, oh, sorry. No, not a third mirror plane. Here's my table, it's a cyclohexane. The mirror plane goes through the table, but my 2 methyl groups are like this. So if the mirror plane comes this way, the top has to equal the bottom. Methyl groups are up, there's no methyl groups down. So we got 2 and only 2 chiral centers. This one, if you said yes, that it's chiral initially, or meso initially, you were looking at that one. But what does this mirror plane do? It cuts through those 2 carbons, and those 2 carbons are not chiral anymore. Again, if you can pass a mirror plane through the molecule and it cuts through carbons, those carbons are not chiral. So actually a 1,4 disubstituted cyclohexane, unless there's a chiral center outside the ring, the 1,4 can never have chiral centers. At least the 1 and 4 can't be chiral. So, not meso. This one was not meso. Does that make sense? D. Had to work our way back to a Fisher projection. Is that Fisher projection meso or not? Well, what should you check first? If that Fisher projection was to be meso, what would have to be true? Because the mirror plane's got to go through the center of the molecule. So what about the top 3 groups and the bottom 3 groups? Has to be true if it's going to be meso. Same 3 groups attached to the top carbon that are attached to the bottom carbon. So now if I give you 2 Fisher projections and I say, are they same enantiomers, diastereomers, or meso? The first thing you have to do is to check the 2 carbons and make sure that they either do or don't have the same 3 groups attached. So the top carbon's got an H, a Cl, and a methyl. The bottom carbon has an H, a Cl, and a methyl. It could be meso. Could be meso. So now we have to check and see, is it meso? Yes or no? Not meso? Absolutely. So in other words, in this conformation, the molecule might not be meso because there's no mirror plane, but it still could be meso. So in other words, what we have to do is we've got to rotate the groups and see if we can line them up to get that mirror plane. If we can, it's meso. If we can't, it's not. So if I try and rotate the groups, can I make this meso? And if I can, it is. So what do you want to line up? Okay, so rotate it this way. Okay, so if I do that, the chlorine is down, the methyl group comes over here, the hydrogen comes over there, Is there a mirror plane? Yes, and so actually this is meso. So
So we rotate it,
you could rotate the top ones if you want.
we work this couple now.
That doesn't get you anywhere. Rotating the entire molecule doesn't help you.
I just, I mean, like when we're
Oh, I wouldn't. If I had two molecules and I've got the top carbon the same and the bottom carbon the same, I'm not going to really rotate it because then they're not in the same orientation. So then I don't have any choice but to do RNS, which I need to come back to. So I'm really just rotating, again, I'm rotating like a Newman projection. And what I'm trying to do is to rotate it so the top and bottoms are mirror planes. And if that's the case, I've got two chiral centers and a mirror plane. This compound is meso.
You can do the same.
Yeah, so I'm going to have to modify my four choices. So I'm going to have to modify my four choices. So we're going to have, they're either enantiomers or diastereomers. They are the same meso compound, or same and meso, or they are the same but not meso. So I have to modify those four choices. But in this case, all I did was determine whether it was meso or not. I have one more and then we're going to come back to that. Chair cyclohexane. Meso or not meso? Yes, meso. What else? And what else? What do other people think? Yes, no, don't know, stuck. I got two mesos. Three mesos. Anybody not meso? Anybody can't tell? I can't tell. So let me ask myself, is there any way that I might see this a little bit better? And myself would answer, let's put it in a flat cyclohexane. Let's put this chair into a flat cyclohexane. So how are the chlorines going to be attached to the ring? With what kinds of bonds? If I'm looking down on the ring, the chlorines are going to have what kind of wedge? They're going to have a bold wedge. Meso? Now that I put it in the flat Chiral centers, yes. Mirror plane, yes. That one's meso. So for the cyclohexanes, what we have to do is you have to really write those out as a flat chair or a flat cyclohexane, and then go ahead and determine whether it's meso or not.
So you can do like
The problem is the only place I can cut where the left and right halves are the same as cut through like this. But that's not the right mirror plane. If it's so I should take a step back. Over here we rotated till we found a conformation that was meso. So in conformationally mobile systems, what does that mean? That means that we have different conformations. We have flat chair, flat cyclohexane, chair cyclohexane, different conformations. In a conformationally mobile system, you just have to find one conformation that shows the mirror plane. And if that happens, then it's meso. So over here where we're rotating, we find the conformation with the mirror plane. In a chair, you just have to make it flat. If we can find one that has a mirror plane, it is meso. Do I have another one? I got one more. We haven't done any Newman projections today, so Newman projection. Meso, not meso. I would start with a question of what's a meso Newman projection going to look like? So if I have, where am I going to see the mirror plane? I'm going to see the mirror plane when the Newman projection is eclipsed. And you might say, well, where's the mirror plane? The mirror plane is this way. Newman projection, missing a lot. Newman projection, missing the back. So when this is eclipsed and the groups are lined up, the mirror plane's got to go this way so that when it cuts it in half, these two groups are the same, these two groups are the same, and the back two groups are the same. So the mirror plane in the Newman projection is going to cut through the center of the bond, which we're looking at down the bond. So these two groups are the same, these two groups are the same, and those two groups are the same. If you can put the molecule into that kind of conformation, that kind of eclipsed Newman conformation, then it will be meso. If you can't line up the groups that way, it's not meso. Of course, I'm assuming in all these cases that the front and back carbon are chiral. I'm also assuming that the front and back carbon have the same three groups attached to it. Because if the front and back carbons don't have the same three groups, it ain't ever going to be meso. So, the first thing you check is front carbon, three groups, are they the same as back carbon? Same thing for a Fisher projection, top three same as bottom three. So can I line that molecule on the left up into a form where the methyl's into an eclipsed conformation an eclipsed Newman where the methyls, the hydrogens, and the chlorines all match up. So if I want, let's rotate the back carbon. So let's rotate the back carbon 180 degrees with the hydrogen. So it's lined up. The chlorine's going to go 180 degrees. So it's lined up. And the methyl group's going to go 180 degrees so that it's lined up. So this Newman projection would be meso. Anything short of that, not meso. So I think that's all the ways we've drawn molecules. And so that's all the ways we have to determine whether they're meso or not meso. So if I just go back here, if you like the A's and B's and C's, for the Fisher projection, the molecule has to be able to be lined up like that, where the two vertical positions are the same. No. Hold on for a second. I'm getting too... How about that? Better. So I've got to have it lined up. So there's my mirror plane. So what we've been doing is we've been playing the game, is that single compound meso or not meso? But if I give you a pair of molecules and they're both meso, then they're the same meso compound. If I give you them and they're the same but not meso, then they're the same not meso compound. Sort of with me? So you might say, okay, so if I gave you a pair of molecules, like this, doing R and S will not help. Do these molecules have the possibility of being meso? That's the first question I should ask. Could these molecules be meso? So the top three groups, are they the same as the bottom three groups? Are these three groups up here the same as these three groups down there? So it could be meso. So when it can be meso, doing R and S isn't always going to give you the right answer. Because if we went back and we looked at the two mirror images, they might have both been RR, but then the mirror image was SS, but then they were superimposable because they were meso. So the configuration doesn't rule out that they're the same two meso compounds. So what we should do first of all is determine for these two molecules, are they meso? Which one's meso and which one's not? Or are they both meso? Or are they both not meso? So we should take these two molecules and determine, are they meso or not? So is the left molecule meso? Yes, no? 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 In order for this mirror plane to exist, if I line up two of the groups, the other ones have to be right in place. So the fact is, I lined these two hydrogens up, the chlorine and the methyl don't line up. So as far as this one is not meso. It is definitely not meso. So one of the things I look for is I'm going to try and line the groups up. If I already lined up one of them and the other two aren't there, it's not meso. One on the right. It's not meso as well. Why? Because in terms of making the mirror plane, the two hydrogens are in the positions they need to be in. But then the chlorines have to be opposite each other in the methyls. So again, I've lined up two groups to try and make it meso, and the other two groups didn't, so therefore this is not meso as well. Well, this is the toughest, this is the kind of problem that normally if I whipped one out, I wouldn't whip out the hardest one. Because take a minute here to sort of sum up. Remember that the relationships between one molecule and another of those four, the most predominant relationship is that they're going to be diastereomers. Because if you're a molecule, you've got 3 diastereomers, but only 1 enantiomer. Sorry, 2 diastereomers, but 1 enantiomer. So statistically speaking, you're more likely to be diastereomers than you are to be the same or enantiomers. In this case, what would happen if one was meso and one was not meso? If one was meso and one was not meso, how did I make it the other molecule not meso? I changed one carbon. So a meso-not meso pair are going to be diastereomers. A meso-meso pair are the same meso compound.
So before we do those
I could, but I'm going to get the same answer. I'm going to get the same answer that they're not meso. Because these are Fisher projections, they're already eclipsed. Because, yeah, Fisher projections are already eclipsed. So that means I lined up these 2 hydrogens, but I can't line up the other 2 sets of groups. Or they're the same not meso compound. So meso not meso diastereomers, meso meso same meso compound, not meso, I've now got to see, are they the same but they're not meso, or are they enantiomers? Are they that DL pair that I talked about earlier? So the idea here is, and we'll kind of finish this up, and if you have any questions, what I'm going to do is I will put in today's folder, I'll put there's a whole bunch of these problems of matching, and you'll see on, like, if you're anticipating next Monday's exam, it's only Wednesday, but still, what are we going to be doing? We're going to be doing RNS. I'm going to give you a couple molecules and say, are they meso, not meso, same, and then enantiomers. I am strongly thinking about going back and doing the cyclohexane chair conformations and the Newman projections again. And I'll have your exams. I'll have your exams either tomorrow or I'll scan them in and send them to you later this afternoon. If I hadn't have gotten caught up for 6 straight hours of trying to fix this instrument, I would have had it done. It's partially fixed. So, if you're thinking about that, I'll put some problems in the folder so you can start doing this. But we'll kind of finish this up tomorrow. And then we're going to go back to the first part of chapter 6 and finish up the alkenes. And then we'll start talking about chapter 7, which I released this morning. We'll start talking initially about SN. It'll be substitution reactions. Just the first couple of sections. So for 7, what I would, just the first maybe like the first 3 sections. But I'm probably going to end up lecturing on that and then going back and reading it might be. So in other words, hearing the lecture first and then reading it the second would be okay. But I'm anticipating the exam is going to be RNS, different types of stereoisomers, and then, like I said, the cyclohexanes and the Newman projections. And you can probably guess why I'm doing that, because I think we need additional practice on Newman projections. Well, alkenes probably will be, because you'll see it's just an extension. It's an extension. My years of experience of teaching tells me that if I say that the chapter 7 stuff will not be on the exam, then when I get to chapter 7 stuff tomorrow, everybody's going to zone out. So I have to say yes. And if I say no, I say it at the end of class, after everybody's done zoning out. So there'll be some basics on chapter 7. I mean, chapter 7, SN1, SN2, E1, and E2, those are the 4 big areas of organic, and we're going to take some time to do that.
So, you possibly put in stuff
It's for exams purposes. So in other words, I might give you a problem on cyclohexanes to have you do that on the second exam. And so that when you take a look at your exam, if you did poorly on that, you're going to want to do. My goal is to make sure that my goal is to try as best I can so that you can do those kinds of problems and understand that. And so when we do have a lot of sort of mistakes on those problems, I like to put them back on again, so that way you've got to sort of master that. You can come and see me. What I'm going to do is I will put the answer key I'll put the answer key in Monday's folder. And then you can go ahead and check your answer key, and then if you have any questions, email me or come see me. I'm going to put the exam in Monday's folder because that's where the exam started out. I mean, I can, when I send the email, maybe I'll just attach it and send the exam out to everybody, but I haven't. It's not going to take me very long to finish up the grading. There's only 12. Normally I'm doing 60 to 65. At a time. It's an entire weekend. the grading tests. So this seems easy, except that this instrument, new student orientation, you don't need to know that, but that's what's been stopping me from finishing it up. So I'll have those, and like I said, I may just snip them and scan them to you so that you have them today. But I do want to go, but I do think I want to go back to having a couple, a cyclohexane problem and a Newman rejection problem, so that I can make sure that we've got that under control. That's what we're going to do tomorrow. So we need to do cis-trans of alkenes. We need to name alkenes. We need to do cis-trans alkenes, and we need to do EZ alkenes. EZ alkenes require us knowing the Kohn-Engel pre-log sequence rules. So I skipped ahead of that, and now I'm going to go back because hopefully, if we can determine 1, 2, 3, and 4 well, it'll be a piece of cake to do E and Z. Maybe will truly be easy. So we'll go back, and that's what we'll talk about. But we'll finish up with this tomorrow. Any questions you have on this? So I am going to put those problems in. I will put some problems in, and they'll have answer keys and everything else. So if you were going to read ahead, I would read beginning of chapter 6 and the first couple sections of chapter 7. But the way I'm going to present it, I'm just going to kind of lecture on it. So, oh yeah, I read that in the book, or you can just read the book afterwards. And again, when I put a PowerPoint series of notes in there, the video goes with the PowerPoint. So if you wanted to watch a video ahead of time, feel free to, because they'll be there. You can watch it before or after, at whatever speed you'd like. All right, so see you tomorrow. But if you have any questions, by all means, shoot them my way.